All right, so welcome back, Genius. So in this session, we'll be talking about the unsigned and the signed and the unsigned integers, and also the two other integer representations. So basically, we have seen more of signed and unsigned integer, but let's take a look at it deeper and understand better. Okay. So what are unsigned integers? All right. What are signed and unsigned integers? Both signed and unsigned integers are used to represent whole numbers. Okay, we already know this. So these are used to represent whole numbers, but the main difference lies in how they are being represented and how they represent it. The signed integers represent both negative and positive numbers, while the unsigned integers only represent positive numbers. Okay, and again, the difference lies in how the bits are being interpreted. So when we have an 8-bit unsigned integer and also an 8-bit of signed integer, the way that these integers are interpreted, these bits are interpreted are very, very different. Okay, so now we are going to explain that as we go on. So with the signed integers, they can represent both positive and negative numbers. We already know this. Now, to do this, one of the bits, now the bit that we call the most significant bit is reversed to represent sign of the number. Now, look at it. Sign integers represent both negative and positive number. That means they represent signed numbers. Okay? Now, they represent signed numbers. Then, we now use one of the bits. If we have 8 bits, that means we use one of the bits to represent the sign. So the one of the bits will tell us, is it a negative number or a positive number? So let me bring up my board. I'll have to bring this. Okay. All right. So I have so I have an 8-bit unsigned integer 1 0 0 1 1 1 1 0. All right. So this is an 8-bit integer. All right. This is an 8-bit integer. So we have 1, 2, 3, 4, 5, 6, 7, 8. Now, the most significant bit is the one right here. All right, this is the most significant bit, the MSB. All right, so this is the most significant bit, right? This one. So with this most significant bit, we are using this to represent the sign. All right, it represents the sign. Is it positive or negative? So now, how do we know whether it's positive or negative? Now, whenever we have something like this, the most significant bit for the sign integers are used to represent the sign. So if the bit is 1, that means the integer is a negative number. But if the bit is 0, that is a positive number. You understand? So we have 8 bits. We use one of the bits to represent the sign. If it is 1, that means sign is negative, and if it is 0, that means the sign is positive. So we now use the remaining 7 bits to calculate the value that it can hold. Right? Okay. So let's go back to our slide. Now, when the most significant bit is 0, that means the number is a positive number. When the most significant bit is 1, that means the number is a negative number. Do you understand? All right. So the most significant bit is the one at the leftmost bit. Okay. So and this signed integer, they are stored as 2's complement. All right. We have another representation that we call the 2's complement. We'll talk about it later on and explain what we mean and how it works. Okay, but these integers are stored as 2's complement integers. All right. So now the most common method of representing signed integers is 2's complement, which allows for efficient binary arithmetic and simplifies hardware design. Now, when we want to represent or store signed integers, the format that we use to store it in the computer is 2's complement. The unsigned integers are stored like that. They don't need to be stored as 2's complement. Okay. So now, what is the range of signed integers? Now, for an n-bit signed integer, all right, this n can be 4-bit, it can be 8-bit, it can be 16-bit, it can be 32 bits. Okay. For an n-bit signed integer, the range is minus 2 raised to power n minus 1. Remember, n is the number of bits. So minus 2 raised to the power n to 2 raised to the power n minus 1. Right? So now let's do this calculation. Let me show you what we mean. So if you want to calculate what is the range, all right, can this signed integer take? It depends on the number of bits that we are using. Now let's say we already have an 8-bit integer here. Okay, let's go for, we have an 8-bit integer, 1, 2, 3, 4, 5, 6, 7, 8. All right. So we say that the range, if you want to calculate the range, now we have the range is minus 2 raised to the power n minus 1 to 2 raised to the power n minus 1 minus 1. So let's do the calculation now. N is what? 8, because we have 8 bits here. So we say minus 2 raised to the power 8 minus 1 down to 2 raised to the power 8 minus 1. Then whatever we get to, I'm going to see, this is 8. Yeah, this is 8. Then minus 1. So 2 raised to the power 8 minus 1 is 7. So 2 raised to the power 7 is minus 127. All right. Minus 127. Sorry, minus 1 raised to the power 7 is 28. I'm sorry about that. All right. 2 raised to the power 7 is 128. So the range is from minus 128 to 2 raised to the power 7 here is also 128. Then 128 minus 1 give us 127. Do you understand? So it means that if you have an 8-bit signed integer, all right? So if you're declaring any value in your programming, when you're in your program, and you say that this is a signed integer, and it is 8, you use the int 8. I have shown you that you put it in 8 or byte, all right? This is an 8-bit. So you can only say, you can only store value within this range. If you store anything, if you store minus 129, all right, there will be an overflow. All right. If you store 128, there will be an overflow. It means that the signed byte or the signed 8-bit integer says I cannot store anything from minus 129 upward. I can only store from minus 128 downward down to plus 127. I cannot store anything 120. 128 is bigger than me. It's as if you have a 4 liters gallon and you're going to fetch a 5 liters of water. There will be an overflow. Okay, so it cannot take it. Do you understand? It cannot take it. All right. So now this is how you get range. If you don't understand this, please reach out to us. All right. So now 8-bit signed integer. That's what we have already just done here. All right. It is between minus 128 to plus 127. I've just shown you that. But for 16-bit, just do the same thing. Here the n will not be 16. So 16 minus 1 will be 15. So 2 raised to the power 15. All right, that's what that will give you this one. Then 2 raised to the power 15 minus 1 will give you this one. All right. So this is how you do it. That 2-bit is the same thing, 64-bit is the same thing. But for the unsigned integer, we only represent positive value. We don't represent negative values. So we only use the whole bit to represent positive value. That means this unsigned integer will have a wider range, especially when it comes to positive value. It have a wider range that can cover. So unsigned integer can represent only non-negative numbers from 0 upward, only non-negative number, although it still has its own range. It has its own range based on the number of bits we are using. All right. So all bits are used to represent the magnitude. But for the signed integer, the first bit is used, the most significant bit is used to represent the sign. Then the remaining 7 will not be used to represent the magnitude of that value. But for the unsigned, we are not considering negative values. So there's no bit used for the sign of that number. Okay. MSB is not treated as a signed bit, all right? The MSB will not be treated as a signed bit. and all values are treated as. So when you're working with unsigned integer, you can never have a negative number in it. So if you try to go and say and add any negative number to unsigned integer, there will be an error. Right? So what is the range of unsigned integers? All right, it is between 0 to 2 raised to the power n minus 1. All right, so let's go to the board and do something. This time around, we are looking at unsigned integer. So we are no longer considering any negative number, and the range is 0 to raised to the power n minus 2 raised to the power n minus 1. Okay, I don't think this. So what do we do? 2 raised to the power 8. 2 raised to the power 8 minus 1. And then we'll have 256, right? Minus 1 will give us 255. Do you understand? So the range of an unsigned integer that is an 8-bit unsigned integer is from 0 to 255. So as simple as the n is the number of bits, just do 2 raised to the power 8 minus 1, and you get the range. So this is the range. So if you try to say, if you try to store 256 to an unsigned 8-bit integer, there will be an overflow. And if you try to store a minus a negative number, all right, there will be an overflow because it's not within the range. You can only give them what they can carry. Don't give them what they cannot carry. Okay. All right. So example is 8 bits will go from 0 to 255. I've just shown you 3 bits is the same thing. All you have to do is to replace this n to be 16 and it'll be on negative. All right. And so on. So what is the key difference between signed and unsigned integers? Basically, let's take a look at them based on some features. When we talk about the range, signed integers include negative and positive numbers. The range of signed integers include both negative and positive numbers, but the unsigned integers only non-negative numbers. They don't negative numbers. We also look at the signed bit. For signed integers, the most significant bit is used as the signed bit, but for the unsigned integer, there is no signed bit. We don't have this thing like signed bit for the unsigned integer. Everything is considered to be a positive number. For the use cases, signed integers, they are used when you put negative values are needed. So whenever you're working with negative numbers, that is where you use signed integers. All right? Don't worry, as we start programming, you're going to see all these things. In this course, you'll be learning C and C++ programming. So you're going to see how these things come to play. All right? It's very, very interesting. Okay, don't get discouraged. So we also have the mass value. Okay, the signed integer, the mass value, when it comes to maybe the positive number, is lower because we are using the signed bit. We are using one of the bits as a signed bit. All right? And then for the unsigned bit, it is higher because we are using all the bits to get the magnitude of the value. Okay? Right? So why should you use unsigned integers? Why and when should you use unsigned integers? For memory efficiency, whenever you are very sure that the integer value that you want to store, it will never be a negative number. Always use unsigned integers. Always use unsigned integers because it will help your computer your memory to work efficiently. Now, this is the reason why we said you should take this course. Now, as a programmer, you might just go and use an unsigned integer. Let's say you're programming in C++ or you're programming in C# or in any of the programming languages, and you now go and use signed integer where you are not going to be, that number will never be a negative number. You can see that your memory efficiency will be poor. All right? So this is the reasons why we are teaching you this. Some of you will be like, you don't need, you need to understand how these things work. To make you a better developer, a better programmer, a better cyber security, whatever you want to be. The things to learn here will actually make you better. For logical representation, all right? When you want to, if you have any, you want to count the number of times something is happening, you can never use signed integers. You will always use unsigned integers because your counts can never be negative. Sizes of something can never be negative. Indices, memory addresses, all these things can never be negative. So you have to use unsigned integers because unsigned integers will only contain negative. So when it comes to bit level manipulation, it is easier to deal with unsigned integer. All right? Okay. So let us take a look at some of the representations of integers in binary. So when working with binary numbers, especially in low-level programming, C# sorry, C and C++ are low-level programming down to this. So integers are typically represented using one of these four formats. It can be unsigned magnitude representation or signed magnitude representation. We have seen this one. We also have the one we call one's complement representation, and also called the one we call two's complement representation. You see, this one's complement representation and two's complement representation, they have to do with working with signed integers. All right, they don't have anything to do with unsigned integers, because as we go on, you're going to see why we have the one's complement, because we will have one's complement because we want to get the negative value of a positive number. So this one's complement has one's complement and two's complement, they have to do with signed integers. But as we go on, you're going to understand why we no longer use one's complement. Two's complement is a better representation of integers. So we are going to see. So the first thing we treat here is that each of these has its own method for representing positive and negative numbers, and they vary in terms of ease of use, efficiency, and hardware implementation. All right. So the bottom line is, whenever you're working with positive number that can never be negative, number, always use the unsigned integer. If you're working with anyone that could be either positive or negative, then you're going to be working with signed magnitude representation, signed integer. But even your signed integer, they are stored in the computer as two's complement representation. So let's go and see. So let's talk about the one's complement. Now the thing is, this is the concept. Positive numbers are the same as unsigned binary. Do you understand? So when we want to count from 1 to 15 or 16, all the positive numbers are the same thing with the unsigned binary integers. They are the same. But we will now want to know the negative numbers are represented by all base of the positive versions. Okay, now let me show you something. When we have something like this, okay, I will just have to use this. I'm going to be using the 8-bit. When we have something like this, or maybe I should just make it 4-bit to be easier about the right? Okay, no worry, let me leave it. Let's keep working with the 8-bit. Now, for the okay, I'll have to make this thing positive. Remember, if the most significant bit is 0, that is a positive number. Remember. So I really don't know what the number is until I convert, but I'm not going to convert this number to know the decimal value. But until I convert it, I'll know the decimal value. But then we are very sure that this is a positive number. So using the one's complement, we want to get the negative numbers or positive number. Remember, we don't have any issues with the unsigned integers because they are all positive. But when you now want to work with signed integers, you need to get the negative values. So how does the computer calculate the negative values, the negative of these positive numbers? How do computers calculate it? One of the ways is using the two's complement. Another way is using the one's complement. But let me show you how the one's complement works. If I want to find the negative of this positive number, let me use the one's complement. So for the one's complement, the idea is invert every bit here. So if it is 0, take it to 1. If it is 1, convert it to 0. So for the negative one's complement here, 0 here will be 1, 1 here will be 0, the 2 zeros will be 1, 1, and then this one will be 0, 1, 1, 0. Now this is for the one's complement. This is one's complement. This is one's complement, all right? It is as simple as inverting the bits. So this is the one's complement, all right? All right, this is the one's complement. We have a positive number here. This is a positive number. So if we want to get the negative number of this number, we will have to flip the bits. So here we inverted the one to be 0 to be 1, 1 to be 0, 0 to be 1, 0 to be 1, 1 to be 0, like that. So in the one's complement, this is the negative value. the negative equivalent of this guy. All right. But to show you why this is very bad, let me get a shorter bit. Let me work with 0. Let me work with 2 2. So 2 will be 0, 0, 1, 0. So this is the binary representation of 2. Now, with the ones complement, it says that if I want to get, this is plus, right? It says that if I want to get -2, I will have to do it. So I will say 1, 1, 0, 1. So this is -2. Now, the problem we have with the ones complement is that this is not a good representation of it. Now, let me show you the problem. If I do 2 plus 2 minus 2, I'm supposed to get 0, right? Supposed to get 0. And the 0 representation, the final representation of 0 is this. All of them are 0. All right? So now let's do this. Let's do 2 plus, 2 minus 2. Let's do this arithmetic. Final arithmetic. Don't worry, we'll do arithmetic operation in the next section. Okay. So 2 minus 2 should be 0. All right. Now, remember this is plus 2. All right. But because I'm not shown you how to do subtraction. All right. I'm going to change my format. I will say -2 plus 2 is still the same thing. -2 plus 2 will still give me 0. It's still the same thing. So now, this is the one I'm going to work with. I'm going to work with this one. So I will now say, what is minus? The minus 2 is this one up here. So I will say 1, 1, 0, 1, then plus 0. I will say 0, 0, 1, 0. So this is supposed to give me 0, but let's do it. 1 plus 0 will give me 1. 0 plus 1 will give me 1. 1 plus 0 will give me 1. And 1 plus 0 will give me 1. What's happening? This is the actual representation of 0. This is 0 again. That means this is not 0. You can see where we are having issues with the ones complement. When it comes to arithmetic operations, the ones complement has a lot of disadvantages. But it's actually better than signed magnitude representation, but it is failing here. This is not correct. And imagine that your computer is now doing -2 plus 2, and you're not getting 0. Again, there's an error. So with the one complement, we are having an error here. All right, but it is very simple. Clicking the piece to get a negative number of a number. No, but that's not really correct. There's some errors with it. For example, if you have a decimal number of 5, so if you want to get the 2's complement of it, you flip all the bits and get it's just an inversion of all these things. But you have seen that it is not efficient. The pros is that it's very slightly easier arithmetic than sign magnitude, but it's very simple. Just invert the logic and you get it. Now, but the thing is that the problem is that it has 2 representations of 0. We never have I have not seen anything like -0. There's nothing like -0. But with the 2's complement, with the 1's complement, it has 2 representations for 0, plus and minus. And you can see that is what we had here. Do you understand? Now, look at it. What we got here is actually 0. In the 1's complement, this is 0. But this is -0. There's confusion. Now, this is +0. This one is +0. But this one is -0. Which one are we now going to pick over each other? There's nothing like that. So that is why the ones complement is not efficient for arithmetic operation. You can see it has 2 zeros, and when you try to do an arithmetic operation, it gives you a wrong number. It actually gives you a wrong number. Okay, so that is where the 2's complement comes in. So the 2 complement was also created to solve the problem. So how does it solve this problem? The positive numbers are still the same thing with your sign binary. All right, +5 is still the same thing with +5. All right, but the negative numbers, what we do is we still do the inversion we'll invert all the bits, but instead of stopping at the inversion, we will add 1 to it. All right. So example like this, we have +5, and this is +5, -5. We will invert all the bits. After inverting all the bits, we will now add 1 to it. So let me show you. So let's go on with this, what we in this our board, what we had before. So I'm going to erase all these things. Okay, so so I will have I'm still working with 2, 0, 0, 1, 0. I still have 0, 1, 0. Okay. So now we have this is +2. All right. So in the 2's complement, we will do the same thing. We'll flip. So we'll get 1, 1, 0, 1. But we don't stop here. All right. This is the 1's complement. All right. This is 1's complement. All right. So we don't stop here. What we are going to do is that we will add 1 to this guy. All right. So we'll say this is 0, 0, 0, 1. So this is the binary representation of 1. So this is where we now get the 2's complement. All right, the 2's complement. So when you do this, you will now get 1 + 1 is 2. So we'll write 0 and we'll carry 1. Don't worry, we'll do arithmetic in the next session. I will teach you how to do arithmetic in binary. All right. So we have carried 1. That 1 we'll put it here. So 1 + 0 will give us 1. 1 + 0 will give us 1, and 1 + 0 will give us 1. So now this is -2 in 2's complement. But in 1's complement, this is -2. And we have seen that we did arithmetic calculation here, and there was a problem with the 1's complement. So let's try the same thing with the 2's complement. So we'll say we're going to do -2 + 2. It should give us 0. So -2 is 1, 1, 1, 0, then plus 0. Sorry, let me think here. So I will say 0, 0, 1, 0. So this is -2, and this is +2. So it should give us 0. Now, 0 - 0 will give us 0. 1 + 1 will give us 2. But since it is base 2, we'll write 0, convert that 2 to 1, add that 1 here. 1 + 1 will also give us 2. 2 + 0 will give us 2. We'll write 0, carry 1, add here. 2 + 0 will give us, then we will now have something we call carry. We'll explain this in the next session. Now, this is called carry. So for now, we will ignore it. All right, we will ignore it. So this is minus, this is 0. All right. -2 + 2 is supposed to give us 0, and this is the correct answer. Do you understand? So with the 2's complement, it is fine. All right, there will be no error. So that is why computers no longer use the 1's complement. They now use 2's complement to represent signed integers. All right. Okay. So we only have 1 0. There is no 2 zeros. I have a table that I'm going to show you all these things just in a minute. So in 1's complement, we have 2 zeros. But in 2's complement, we only have 1 0. All right. Arithmetic operations are straightforward and they are efficient. All right. You can see what we just did now. -2 + 2 gave us 0. That's the right answer. Okay. And it supports easy overflow detection. We'll talk about overflow in the next section. All right. We'll talk about overflow in the next section. All right. So, but what are the issues? They are more complex to understand initially. If you watch, we have to do extra steps to get here, but it's not really bad, right? We have to do one extra step here. Do you understand? We have to do one extra step here. But the 1's complement was just easy flipping or inverting the bit. But here, after inverting the bit, we now added 1 to it. So it is somehow more complex, but is better. So what is the range? The range is still the same thing with whether the sign bits, all right, minus 2 raised to power, minus 2 raised to power n minus 1, blah, blah, blah. So this is the range, okay? So now let us take a look at the table, all right? This is 0, all right? For unsigned, signed, all of them are 0 like this, okay? All the positive numbers, for all of them, both unsigned, signed, and everything, the positive numbers are the same, all right? They represent, if you can see, all of them are the same, all right? So you can see, but when we now got to 16, for the unsigned bit, when we got to 16, so this is the representation of 16 for unsigned bit. But remember, for the signed bit, for the signed integer, all right, anything that starts with 1 is a minus. Do you understand? Anything that starts with 1 is minus. But for the signed bit, for the unsigned, we are not considering anything negative. So you can see, instead of this thing to represent 16, it's representing minus 0. All right? And here, this guy represents minus 15, the one's complement. And here, this guy represents minus 16 in the two's complement. So when we go to the next table, all right, as we go on 17, now for the unsigned, this is 17, this is minus 1, this is minus 14. So it goes down, and when we get to, you can now see for the signed and one's company, both of them have minus 0, two zeros. They have, both of them has 2 representation of zeros, which is bad. All right, but if you look at the two's complement, there's only 1 representation of 0. So this is the two's complement is the data is the signed representation for integers in modern computers. Okay, so if it sounds confusing, don't worry. You can just take your time and rewatch the video again and grab more. All right, and if you get confused, please reach out to me, reach out to us for more explanation. Thank you very much, and I'll see you in the next class.